Hello, everybody, and welcome to our experimental design lecture in the Autonomous University of the State of Mexico, the School of Engineering, and we are in the artificial intelligence career. So we are now going to have our class for today, which is Monday, the 1st of June, 2026. And we are going to talk about the very last subjects of our lecture. So let me share my screen. Okay. 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 So I am going to put here the name of the file. Save as. Here downloads. So I am going to put here experimental design lecture 1st June 2026. Okay, perfect. Okay, so let us put here the data of the lecture. So it is the experimental design, lecturer. My name is David Joaquim Delgado Hernandez. The program is the Bachelor in Science in Artificial Intelligence at the Autonomous University of the State of Mexico. The duration will be 3 hours, 180 minutes. Language will be in English. And today's date again, it is the 1st of June, 2026. Okay, so let us save this. Well, what is the first subject that we are going to study subject? It is related with the subject 4.3 in our program, which is the data acquisition and automated experimentation. What is the objective here? Objective. Well, it is to design and implement an automated data acquisition system. Okay. Using, well, in this case, I am just taking the the objective that it is in Dr. Sala's book, the one that we have used to carry out this lecture, but we are going to explain a little bit different things. The Python routines, you can find them in the first files that I shared to you at the beginning of the term, okay? So you can check these Python routines there if you are curious about that, okay? So it is to randomize experimental designs, okay? Ensuring temporal synchronization between treatment signals and sensor responses. Well, this topic it's very interesting because you can actually implement a physical hardware in an experiment in order to get data. Uh, for instance, in the civil engineering area, we can have some devices to monitor the movements when an earthquake affects a building. We can have different sensors installed in the columns, in the beams, in the different parts of the building in order to get information in real time. So let me show you quickly. Uh, for instance, here we can have Texas Instruments bridge live load and earthquake. Okay, here. So because of rights of the author, I cannot play the whole video. I cannot play because otherwise I am not going to be able to upload this class in my YouTube channel because YouTube is going to detect that I am using this video. So let me just put some images for you. So look, what they did was in Nevada, in the United States, they carry out an experiment in the laboratory of civil engineering. And what they did was that they built a bridge, and in this bridge they put some trucks at the very top of the bridge. So let me show you the trucks uh, here. So you can see that the bridge was built in the laboratory, and they put these trucks in order to simulate the traffic flow that it is actually going through any bridge on the street, right? So what they did was that they put these loads in the box of the truck. As you can see, this blue bag is at the rear of the truck, and you have so many different trucks, and they are with this this is overweight, okay. The idea was to have uh, different weights of the trucks, and that these were very heavy trucks in flowing in the bridge. But what they did was that they put these sensors, they put physically the sensors in the columns of the bridge, and they start monitoring in the computer the behavior of the bridge. So here the analyst is looking how these measures are going to the computer when they are carrying out the experiment in real time. Okay, so they are able to get the information from the experiment directly into the computer, and they have these red lights and green lights on the screen where they can see whether there are some variables that are in the correct value, and whether there are some variables that are out of the expected value. So for instance, if you have a red light here, that means that this variable is not going so well. Okay. In contrast, when you have a green, that means that this variable is going okay. Perfect. So at the end of the day, they are able to use these physical devices and put them in the experiment, so they can read automatically the information in the computer, and with that information they can carry out all the things that we have been looking at in this very course. Okay, so that is the idea. What they did was that they started moving this bridge, simulating a very heavy earthquake, and then they get all this data from the different computers, and this is sponsored by National Instruments, which is a trademark in the United States that sells all these devices to get the data. Okay, we are not going to do that here in the lecture, but I wanted to explain what is the meaning of this subject. Okay, so in the first objective, the point is precisely to analyze this kind of thing. Okay, and this is the very first topic for today's lecture. Okay, so how can you get data automatically from an experiment in real time when you are in the laboratory? Okay, that is the first topic in today's class. Okay, so let us now look at the second point, which is 4.4. It is selection of experimental theory. Okay, so what is the objective here? The objective is to evaluate and select the most efficient experimental theory based on the system's dimensionality, dimensionality, linearity, and current knowledge. Level, ensuring a high information density. Okay, for artificial intelligence model training. Okay, perfect. So this is the second topic. Basically, we are going to learn uh, how to select the best type of design of experiment in order to carry out um, some trials in the laboratory or the computer or in some way such that you have an artificial intelligence model training. Okay. The next topic it is 4.5, which is again very similar to the previous one. It is the selection of theory and case study resolution. Okay, what is the objective here? Objective, it is to detect the appropriate experimental design method for instance, full factorial or response surface method versus response surface method to resolve the case study. Well, this case is particularly used in the book to resolve the case study in the book. Okay, we are going to use it to carry out some examples different that the one that is in the book. So this is the third topic for today's lecture. And finally, the fourth topic, it is called 4.6, which is the interpretation, evaluation, and artificial intelligence integration. Okay, what is the objective here? Objective, it is to quantify the impact of experimental design, the final performance of an artificial intelligence system evaluating model fidelity and robustness to ensure that that the hardware software integration is safe and efficient. Perfect. So that is the very last topic, not only for today's class, but for the whole course of experimental design. Okay, so we are going to finish our course with this last subject, this last topic, and well, that will be it. The next step will be to carry out the second partial evaluation, and that's it. That we are going to conclude with the experimental design lectures. Okay. Well, so let us start. Let us start. Here the question to answer is, um, how do I know when to use, for instance, a full factor design, a fractional factorial design, or the as we saw last lecture, the response surface method? That is the question to answer here. Okay. Okay. So let us put an example introduction. So uh, imagine that we are building an artificial intelligence controlled drone. Okay, so let us put here an image. So here is the image. So you are going to design this drone, and it will be controlled by means of artificial intelligence. Okay, perfect. So in this case, the flight time is affected by the following aspects. So let me put some bullet points. Here we are. So for instance, you can have the battery voltage. You can also have the propeller size. Okay. Another thing will be the motor speed, and the other will be the weight. Okay. So you have at least 4 different factors involved in this experiment. And the question is how many experiments would you run? How many experiments will you run? So somebody can say, well, I will run 2 experiments. Another person can say, I will run 10 experiments. Some other could say, I will run 20 experiments, and so on. But the fact here is that if we do this randomly, we are going to spend a lot of money carrying out these experiments, because it is not just a matter of saying, I will run 20 experiments. Okay, how much will it cost? How long will it take? How many days? Okay, how many weeks, or perhaps how many months I am going to spend carrying out these experiments. So in order to avoid this expense, and to make things cheaper, you have to design an experiment. So here you should take into account the following. So if you have many factors, let me put a table. Insert table. Factors. Then you can have here the design of experiment, which is acronym is DoE, design of experiment. Somebody uses this not as a capital, but as a usual letter. And then you can have here the objective. Okay, so let me put this in a beautiful way. Okay. If you have different many factors, you can talk about more than four. More than four factors. And you can use a let's put fractional factorial design. So here you are going to keep only important factors. Okay, because look, if you have, for instance, five different factors, so let us put here 2 to the 5 power. Let's put 5. 5, okay. This is, let me put here, this equals 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. So that will mean that you have to carry out 32 different experiments if you have more than 4 factors, okay? So here it is convenient to use a fractional factorial design because you are going to cut in half. Instead of having 32, you can have only 16, or even better, you can have only 8 different experiments, okay? So if you have 3 or 4 factors, you can use a full factorial design, okay? And here you can identify the important factors, okay? But if you only have 2 factors, then you can use the response surface method, which acronym is RSM, okay? Because here This method will help you to find the optimum value. The optimum value, okay? Okay, so let us save this. Okay, so here are the three different design of experiments that we can use: the fractional factorial design, the full factorial design, and the response surface method. Okay. Well, let us put some example. So, for instance, you are you want to try a coffee in Starbucks. Let us put here Starbucks coffee. Okay. The question here is why does coffee taste different? So, what are the factors that have some influence in this coffee, in the taste of the coffee? So, let us put some things. For instance, you can include here the water temperature. That is one factor. Another thing that you can consider is the coffee amount. For instance, last year I went to Italy, very close to the Rome capital city. And in Italy, all the afternoons they used to have a cup of coffee. But this coffee is very concentrated and the cup is very small. So when I saw this cup and they say, "Oh, Dr. David, would you like a cup of coffee?" And I said, "Yes, please." And they uh, give me this very small cup of coffee. But when I try it, this coffee, it was very heavy. It is because the amount of coffee is very large in comparison with the volume of the cup, right? So that has an influence on the taste of the coffee. What else? For instance, the kind of coffee. Uh, 2 weeks ago, I went to Colombia, and in Colombia, coffee is very famous. Coffee is very famous. The Colombian coffee uh, is very well known all around the world. Okay, so again, they invited me to have a cup of coffee, and it tastes very different from that of the Italy. The taste. So the kind of coffee is also very important. Here in Mexico, in Veracruz, we have very important coffee producers. So it tastes different from that of Colombia and that of Italy. So the kind of coffee is very important. What else? Uh, you can have, for instance, the sugar, okay? And if you add some milk, perhaps if you add some milk, and so on, you have different ingredients that have something to do with the final taste of the coffee. Okay. So here the question is, let us suppose that you are trying to get the best coffee ever, the best coffee of the world. You want to carry out some experiments, and you want to develop the recipe for having the best coffee in the world. So will you test every possible combination. Here, what kind of experiment will you use? What kind of experiment will you use in order to identify what is the best coffee? Okay. So the answer to this question, the answer to this question naturally leads to design of experiment. Okay. You have to design an experiment in order to have some different combinations, and you can then identify what is the best coffee. Okay. So, for instance, uh, one recommendation here in this particular example would be that first, because you have so many different factors, first you carry out fractional factorial designs, and you only keep the important factors. For instance, if you are carrying out this experiment in Mexico, you forget about the Colombian coffee and you forget about the Italian coffee. You just concentrate on the Mexican coffee. So you are now getting rid of the kind of coffee that will be not a factor anymore because you are only trying Mexican coffee. Okay. Again, you can, for instance, put always the same water temperature, always the same. So you can prepare this in a coffee machine. Okay. So you forget about this variable, this factor. Okay. So in that case, you only keep three, and this will be your factorial design. In order to have 32 different experiments, you now are going to have only eight different experiments. That will be a fractional factorial design. Okay, you reduce this number of factors. Okay, for instance, let's suppose that you carry out the experiments and you finally identify that the coffee amount and sugar are the two factors that have a very big impact on the final taste of the coffee. That will be optimization. Which is the best combination of coffee and sugar? And you will use the response surface method in that particular case. Okay. But look, you have to reduce the number of factors in order to get this response surface method for your experimental design. Okay. Well, do you have any questions so far? Okay. So let us look and with this explanation. Uh, Engineers in artificial intelligence rarely know which variables matter. In this case, design of experiments helps us this, to discover these variables systematically. Okay? So let us put here some examples. When do we use fractional factorial design? So, and let us put here some bullet points. It will be this. Okay. When you have many factors, okay? When you have many factors, the best option, the best strategy is to use a fractional factorial design. Second option, when you have limited time, you don't have so much time to carry out many different experiments. So you just have 1 day, 1 week, and the time is your enemy. So in that case, instead of having a full factorial design with a lot of combinations, you just use a fractional factorial design. And when you don't have money, you don't have many resources, economical resources, so you use this this kind of fractional factorial design. Okay, so let us see an example here. So let me put here. Okay, so let us put here an example. I am going to copy this photo. Okay, example. So here you have a pneumatic actuator. So let me put here. So this is a pneumatic actuator. Pneumatic actuator. Okay, here we are. Okay. So this pneumatic actuator, well, basically, you can use this in industry in some fabrics, okay? And the idea is that with this system, you can easily identify the position, the force, the speed, okay, of different machines. So if suddenly the speed of one machine is getting down, this actuator sends a signal to the operator in order to avoid stopping the production. Okay, for instance, imagine that we are producing cars in a Volkswagen or General Motors manufacture company. Okay, so suddenly one machine starts to slow down the speed. Okay, so immediately a red light announces to the operator that that machine is having some trouble, and this operator has to carry out some maintenance activity or so or something like that in order for the machine to continue working and not stop the production. Okay, otherwise you have to stop the plant and the cars are not going to be finished. So that is the objective of this device, the one that is in the photograph. Okay, so what are the factors that we could consider in this example? Okay, the factors to improve the performance of this pneumatic actuator could be Let me put some bullet points here again. Okay. It could be the pressure. You can also look at the frequency of the rotator, okay? The temperature, the bulb type. You can have the different materials, for instance. You can have the thickness, okay, of the rotator, and so on. So let us keep just these six different factors, okay? So there are six factors, okay? So if you were designing a full factorial design, then you will have 2 to the 6 power, okay? 2 to the 6, it means 64 different experiments. So let me put here as power, here. 2 to the 6 implies, say, 64 different experiments, right? That is a lot of money, a lot of money. And time, obviously, and time. But what happens if you just propose a fractional factorial design? Okay, then you can cut. For instance, if you get rid of, let us put it like this, you have already six, but you take out of the equation two of these factors. 6 minus 2 equals 2 to the 4, which is 16 experiments. Much cheaper. So let me put here this as a power, and let me put this as a power as well. Okay, 16 experiments, which is totally much cheaper. So let us put it like that, much cheaper. Okay, perfect. So let us save this. So if you have so many different factors, you use fractional factorial design. So let me put this in bold. Okay. Okay. So next question. When do we use full factorial design? That is the question. And the response is when the number of factors is less or equal to 4. Okay. When it is important, when you need to know about the interactions of the variables. You are not going to study them in isolated form. You are going to study them all together at the same time, okay? Otherwise, you will have to study factor 1 first, okay? Then factor 2, and then factor 3. But no, here in a full factorial design, you combine the three different factors at the same time, okay? Factor 1, factor 2, and factor 3. All of them are put together in order to get some coefficients that can be important in the interaction of these variables. And here you can carry out a full factorial design when the experiments are cheap. So look that basically the money is a very important factor in experimental design. Okay, money and time. For instance, let us put here an example. The paper airplane, the one that we already have, the paper airplane. So it is very cheap because you just need to have some paper and you can carry out the experiment once and once more, okay? So let me put here some bullet points. And what are the important factors here? You can have the wing length, you can have the nose weight, again, and the launch angle. We already see that in a previous class, the launch angle. So at the end of the day, you are going to have three factors. If you translate this into English, that would mean 2 to the power 3, which is 8 different experiments. So let me put here 2 to the 3, power 3. Here we are, which is 8 experiments, okay? So in this case, full factorial design is perfect because it's perfect option. Because it is not going to be very expensive, okay? You are going to keep the cost down, okay? And finally, let us talk about the response surface method. When do we use RSM, response surface method? Okay, RSM, perfect. Here the answer is, let me put some bullet points. Here we are. So when the important factors are already known. I know that the important factors for the paper airplane are the wing length and the launch angle. So I am just going to experiment with these two factors and no more, okay? Because I know that these are the ones that have a very big impact on the distance, the flight distance of my airplane, okay? And you use this when you need to find the optimum. Okay. Let us put the mouse the example. It is the mouse the car. Okay. So you identify that the two important variables is the wheel size and the other important variables is the arm length. Okay. So what you need is to maximize the distance. In this case, response surface method finds the optimum combination. Okay, so let us save this file. Okay. Do you have any questions so far? Everything is okay? Perfect. Uh, I wanted to show you how to use Minitab, but I couldn't get the license to use that software. Uh, Let me see. I am going to carry out an experiment in real time because again I couldn't get the license for the Minitab. But let us try. This is an experiment, okay? So let me see if I can download it from the official website. And if you follow me, please do exactly as I do on your computer. So I am going to share my screen. So let me put here, download Minitab. Minitab. This is another tool. It's a statistical tool, okay? So look for this, start a free trial of Minitab. So let us try this, right? So I am doing this in real time, okay? Okay. So let us see if there is a Mm, okay. Well, I am going to fill this form with my name. Okay. I am going to fill this in real time. Let us put here this. Okay, academic, Mexico. Mexico. Here, Mexico. Okay, Mexico. Let me send. Okay, they are going to send a email. Okay. I have already received the email. Let me open it. Okay. Mm, my inbox. Here. Okay. Welcome to Minitab. Your 14 days trial period has begun. We hope you to take this time to explore Minitab statistical software on the Minitab solution and check out the. Okay, so I am going to click here. Click here. And let me see, because they sent a second email. Okay. Okay. Well, I suppose that I should write my email here. Okay. But the thing is that I don't know. I think that I will start with my Gmail account. So let me erase this. Mm, Continue. Okay. So I should fill this. Mexico. Here we go. Mexico. Okay. Okay. And here in download, let me see. Start free trial. And I have already put this. Uh, Here, advanced design of experiment. But let me see, how can I get this software for installation? Uh, okay. Mhm. Yes. Education, academic, Mexico. I have already put this. Mexico, Mexico. Here, state of Mexico again. Start your free trial. Again, is to activate support with a link to activate. Let me check. Perhaps it is this one. Click. Ah, okay. Okay, 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 okay. Okay, so let me write a password. If you are following me, perhaps you also receive this notification. Anybody is following me? Is anybody there?
Yes, teacher.
Okay. Are you following me? Okay. So, okay. So let me try this. Okay. I put. Okay, continue. This is a contract. Okay. So presumably at the very end, you have to click on the accept here. I accept. Okay. Okay. And here it is the trial version. Okay. So let me see if I can download it in my computer. Here we are. Okay, and I am going to open it. Okay. Yes. And I am now installing. I am going to put it in Spanish. The point here is that the free license only lasts 2 weeks, okay, 14 days. So by the June the 15th, this license will expire. So you will have to buy the new license. Okay, you have to accept here the terms. All these, let me see, because I accept. Next. Okay. And you choose to start with a free trial, okay? You put here. Next. So let me just see. Okay. Install. Let us wait some minutes. Okay. Has finished. Okay, so apparently it is already in my computer. So let me check. Here we are, Minitab. Click. I have to start session. Okay. And here we go. This is the Minitab interface, the environment. So in this part of the software, you can see very similar table. It looks like Excel actually. And you have up here different options in order to carry out some different calculations, okay? So this is software that is useful mainly for statistical calculations, okay? So let us see. Here in the statistics menu, you have one thing which is called DoE, which is the design of experiment, okay? We are going to carry out, for instance, a factorial design of experiment. So you choose a factorial and then you choose create a factorial design. So you just click here. Okay. So let us try the one that we were studying. And we are going to use three different factors. So let me see. We are going to choose three factors. And we put accept. Okay. Design here in design, it is a complete factorial. And you can choose. Okay, let us put these variables. Okay, accept, accept. Here we are. So let me open this window. Here is the already the experimental design. Okay. So here, let me see. For instance, let us compare. Mm, mm, mm. Let us compare. Okay. I'm going to open this. So here you have different factors. Let us suppose that we are carrying out the example of the paper airplane. And our three factors are the wing length. The low value will be 10 centimeters and the high value will be 20. Then we have the nose weight, which is 0 and 5. And finally, we have the launch angle, okay? In this case, it will be 15 degrees and 45 degrees. So in Excel, we already saw this. We have these different combinations, A, B, C, which are the three factors, wing, nose, and angle. And here are our 8 different combinations. And Here, let us put some distances. Uh, 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 uh. Let me see if I can use one of the previous lectures. Uh, Let me see. Okay. In the here, let me use these values, okay? I am going to use these values in Minitab. Okay, perfect. Okay, okay. So look, Minitab automatically change the order of the experiments, okay? As you can see here, it is not 1, 2, 3, 4, 5, and so on. It is 2, 8, 5, 3, 4, 1, 6, and 7. So the idea here is that you carry out the experiments, you have them in order, but when you are putting the data into the Minitab software, you have to use this information. So let me put here, because look here, this is the different order. So in this case, what I would like to see is here. The first experiment is number 2. So I am going to put the result of number 2, which is 3.0, 3.0. Then the second in Minitab will be 8, which in this case, number 8, it is 6.2. So I am going to put here 6.2, enter. Then the third, it is number 5. I am going to put here number 5, which is 3.1. The following is 4. In this case, by coincidence, the fourth value is the 4. So the 4 is 4.5. The fifth is number 5. Sorry, here it is in already 4. It was, let me check. I don't know how to, let me see, how to look all at the same time, because it is changing. The 2 is 3.0, it's okay. 8, 5 is 3.1, okay. Then the fourth is number 3, sorry. Number 3 is 2.4. Number 3 is 2.4. Here, 2.4. Remember, in order to avoid bias, we need to change the order randomly, okay? Randomly, okay. So the good point about Minitab is the it already proposes you one different order, a random order. So the following is number 4, and now number 4 is 4.5. Then 6 is number 1, which is 2.1. The sixth is 5.0, and the last one is 7, which is 3.6. 3.6. Okay, perfect. So let me make this bigger. Okay. Okay, so let us see. This is the factorial design. 3 factors, 8 different runs, and this is one block, only one block. Okay, so let me now find out where can I run the uh, the actual experiment. Mm-mm. Okay, okay. Factorial. So you put here analyze factorial design. Let us put that C8. Okay, cancel. Let me see how can I run it. Design of experiment factorial. Mm, mm. I would like to carry out both the regression and the ANOVA. But mm, okay, let me ask here. As I told you that I am doing this in real time, but I wanted to show you that there are so different softwares that you can use. Obviously, you have to read the user manual and things like that. So let me put it here. Let me ask. Uh, okay, let me see. Okay. Analyze factorial design. Okay, so let me follow these instructions. Okay. Okay, so it says that I should go to the statistics, okay, design of experiments, okay, factorial and analyze design, okay, here we are, okay. So choose your response. Let's double click on the Okay. I choose this as the response, okay? It is the data that I already put in the Minitab table. So terms. Okay, so I choose this option, terms, and I want all these interactions, A, B, C, A, B, A, C, A, B, C, A, B, C. It is correct, so I accept. And then I have to configure the graphs, okay? So in graphs, okay. Okay, so I choose graphs, and I have to click on the Pareto here, then the 4-in-1 here, and that's it. I put accept, and I put accept. So let us see what happens. Okay, so let me open this again. Here we are. Here is the result. That is the way in which you can use Minitab to carry out the experiment. So as you can see here, it is giving you exactly the same thing as we had when we were studying the Excel or the MATLAB results. So you have these the coefficients, okay, and the R square, and you can have here the combinations and the interactions. And here is the equation, okay? Here is the equation that it provides. And here are some graphics. So this is the Pareto diagram. So it shows the most important variables, okay? So it is telling us that variable A, the first variable, is the most important variable in the flight distance, okay? That means that the wing length is very, very important. And the interactions are not so important, okay? This BC interaction is not very important. Okay. So here there is a data missing. There is a data missing. But what I would like you to see is that, for instance, check. Let me put this like this. Oh, here we are. For instance, this is the equation, and look, we already had some equation, and let us see if there is some similarity between these two equations, okay? So, for instance, here you have 3.73, and here you have 3.81. Then the following factor is 0.94, and here is 0.93, okay? Then 0.43 here and 0.43 as well. 0.735 and here 0.73125. Then 0.2375, which is this 0.2025. Then 0.18, which is this one. Okay. So as you can see, it is very similar model. Practically, it is identical. Okay. So the idea here is that you you can use the very same data in your experiment, and you can analyze it either in the MATLAB environment, or in Excel, or in Minitab, or there is another one which is called uh, design expert. So let me put here. I am not going to download it, but I would like to show you. Uh, uh, uh. Here we go. Another software is called Design Expert, which is this is specifically for design of experiments. So again, you provide the data, and the software automatically gives you back all the information related with your experiment. Okay. Again, you can download a free trial of 1 month, I think. But look, this is the kind of graphs that this software can give you. Okay, well, it has a cost, obviously. That's why I try it during the course to teach you how to use Excel, because Excel is very common tool, and we all have access to Excel because the university has the license. The university bought the license to Microsoft, so we can use it freely. Okay, but again, there are other different tools. Look, and they provide with these beautiful graphs, and this is the response surface. Okay, here we are. Okay. Okay. Do you have any questions? Anything at all? So let me see in the previous lecture. The mouse card trap here. Okay. Let us try this in the Minitab. Again, I am doing this in real time. Okay. I cannot guarantee that this is going to run okay, but I am going to try. At the very end of the day, we are in an experimental class. Okay. So let me experiment with this Minitab tool. Okay. So here I have the data for the response surface, and let me try to put it in the Minitab. Okay, so what I am going to do is, let me save this. Well, save where I am. Save. Oh, here. Let me put this save project. Let me put Minitab experimental design. Save. And let us now open a new okay. This is a new sheet. Okay. So I am going to put here the response surface. So I go to statistics, design of experiment, and response surface. So I am going to create a new design, and I have to choose the number of factors. Okay, so it is 2 factors. Okay, and I put accept. Okay, design. Let me see how many we have here. We have 9. Okay, it is 3 and 3. So let me go back. Number of factors. So let me just see. 2 factors, but each factor. Let me put here 3. Uh, Number of central points we don't have. Okay. So the point here is that I will have to have more experiments here. Oh, let me see if I can cut this. Okay. Oh, oh, here at least you have to have 13 different um, runs or experiments. And in our example, we only had 9 here. We only had 9. Okay, so we cannot replicate exactly this, apparently these experiments, because we need to have more different values. So let me see. Let me see. I will choose this. So I will put accept, and I will put accept. So again, it gives me 13 different experiments, but I don't have that information. I don't have that information. But let us suppose I am going to put some data. So let me just see 38, 32. Okay, it is between 32 48. Okay, 32 and 48. So let me just put some data. I am going to propose this data, but I don't have that information. So we cannot compare with our previous lecture, but let us see what happens if I just put some data here, okay? So let us imagine that I have here 32, 48, 45, 37, then 41, then 40, 39, let us suppose 36, 44, 45. Here I have 39 again, 40, and 47. Okay, again, you have to carry out the experiments in the laboratory, and the Minitab is going to ask you about the results of your experiment, and you will have to put them here, okay? Uh, and again, uh, automatically, Minitab proposes a particular order, which is randomly selected, and you have to put the information in that way, okay? So let us follow exactly the same instructions as the previous example. So I go to design of experiment, which is the response surface method, okay? And I have to choose, this is my output variable. I have to put terms, and I will look for all the interactions, it's okay. And in the graphics, the Pareto regular, and this 4-in-1. Okay. And I put accept. And I put accept. Okay. Here we go. I have the different variables. Remember in our example, let me just put in the same screen. So I move this. Okay. So remember in our screen, in our lecture last week, factor A corresponds to the water cement proportion, and factor B corresponds to the curing time, okay? So that is the meaning of A and B, okay? And here are the coefficients, and here is the R square. In this case, it is very low. And here is the analysis of variance, okay? Here we go. And let me see, here is the regression model. So the strength can be predicted in this particular experiment because it has more data than the one that we carried out last week. So it is more complex, the model, okay? Do you remember that we had this very simple model as a result of our analysis? Here it is a more complex model, okay? It has got 1, 2, 3, 4, 5, 6 different terms. And here is the influence of the variables in the strength, in the response of the strength. And let me see here. Okay, so here is the residual, and it is a very good model, as we can see, because the difference between the actual value and the one that the model provides is not so great. Okay, these are the residuals. Okay, and this is the order of the observations. What else can you find here? Oh, And that's it. That's it. So let me ask. Mm, mm, mm. Okay. Okay, so let me see if I can plot the surface. So here, design of experiments, and here we are, surface graph. Okay, okay, accept. Here we are. This is the surface, okay? This is the surface. And with the data that I provided, again, I just invented these numbers. But with that particular data, that will be our response. So here, let me see if I can move this. No, you cannot move this. Apparently, this is fixed. But you can see, right, that the curing time, when you have more days for the curing time, and the semen water relation is big, you can have the biggest strength. Okay, you can see visually here that corresponds with our surface in last week class. But it has a different shape, as you can see. It has a different shape. Okay. So again, this is the way in which you can use these tools. Okay. So I think that I will ask you if you have any questions. Do you have any question? Okay, so if you don't have any questions, let us put here these final ideas. Okay. Okay. So let us put here conclusions. So bullet points. Uh, there are different tools able to carry out the calculations in design of experiments. Okay. For instance, Excel, Python, MATLAB, Minitab, Expert Design, SPSS, etc. So you can use so many different tools in order to carry out the calculations of the experimental design. Some of them are specifically designed to carry out this kind of calculations. For instance, the expert design is a tool specifically designed to carry out design of experiments. In contrast, Excel is a very general tool, okay? It is not specifically for design of experiments, but it is useful. What is the main advantage of Excel? Well, the point that it is available for all of us, okay? So we can have access to Excel very easily, very quickly. We don't have to fill so many things on the internet in order to receive a license just for 2 weeks and so on. So that's the reason why uh, if you are going to carry out experiments, my first suggestion will be for you to use Excel as a first um, tool. But if you have money to buy the license for some specific software, I would recommend Expert Design. I think that it is the better for this specific topic. Okay, or Minitab, as you can see, it also has already programmed in the environment this design of experiment tools. Okay, so that will be our first conclusion. The next conclusion is that full factorial design tell us what matters. It is the important variables, the important factors. Important factors. Full factorial design tell us what are the important factors. If you remember in the Pareto graph, you can see visually if factor A it is the most important or factor B or factor C depending on the number of factors. But full factorial design is very useful for that kind of exercise. Okay, the next conclusion is that fractional factorial design tell, tells us, here is a S missing, tells us what probably matters. And the response surface methodology tells us how to obtain the best performance. For instance, in the last example, in the strength of the concrete element, response surface was very useful because it provided the best combination to get the best strength in the concrete uh, element. Okay, so that is the point with these things. Okay, so that's it, young people. This is our course of experimental design. Uh, I am going to ask again if you have any question. If you have questions, please let me know now, or you keep quiet forever. That is the phrase. And if you don't have any questions, let me stop here the recording, and I will be back to you in a minute.